Hello again, students. This is part 2 of videos where I'm doing problems on calorimetry and heat transfer and phase changes and the things you're doing in the homework problems. I've already gotten an email from someone doing homework 4. I realize there's some stuff that I'll address in another video. But last time we just did specific heat and thermal expansion. This time we're going to set up a calorimetry problem, and it's shown here in our picture. Right? We have, I'm moving this around, try to get it in view. Alright, so we're going to have about a liter or a gallon of water. Alright, it says 1.28 kilograms. Alright, so it sits here. And we're going to put in a piece of steel. And that's 215 degrees Celsius. And the water's at 10 degrees Celsius. Right. So we just note the numbers that we have. 1.28 kilograms at 10 degrees Celsius, and our coefficient, our specific heat capacity for water is 4186 joules per kilogram degree Celsius. So for the steel, all right, we have the mass of the steel is 0.385 kilograms, and its temperature initial, right, its hot temperature is 215 degrees Celsius. And for steel, we have to look up what its coefficient is. And so if I was, pulling out, the table, this is the table from OpenStax, there's one in your textbook, and we're looking for steel. Oh, this is the latent heats. Sorry about that. I want the calorimetry one. So we're going to look. Iron and steel. Alright, 452 joules per kilogram degree Celsius. And you look at that and you're like, well, water's about 9 times as good at holding heat. So what you expect is the water's going to extract all of the heat out of the iron, and the temperature's not going to be that high. That's the point. You're cooling off a piece of iron. All right. So these are our numbers. We want to set this up, and generally for calorimetry, what we want to do is go from, we want to set up a delta T is going to be T final minus T initial. Sometimes what we want to do is say T hot minus T cold, but here we're going to do T final minus T initial, and we want to set up an equation such that the energy that leaves the steel, well, it's going in the opposite direction as when it goes into the water, right? It goes out of the steel, goes into the water, so it's going to be minus the heat that goes into the water. That seems a little counterintuitive, but what will happen is if you don't have that minus sign there, you're going to get, doing final minus initial, you're going to get some sort of equation that gives you a temperature that's not in between, right? This is going to say that I put the hot steel in the water and I get like 400 degrees Celsius or minus 40 degrees Celsius. And that just doesn't make sense. The equilibrium needs to be at my, between my 215 and my 10. All right. So that's where we start out. Q for the steel equals minus Q for the water. And then we just put in, we know that Q is MC delta T, right? Using all the things that we've already used. So the mass of the steel times a specific heat for steel times delta T for the steel. Alright, that's going to have a variable in it. Alright, so move over here for it. Delta T for the steel is going to be final minus initial, so T minus 215 degrees Celsius. We don't know what this T is. That's okay. We're just going to put it in. Delta T for the water is going to be T minus 10 degrees Celsius. Right? And those two T's need to be the same. Right? And so you can kind of reason and see, oh, well, yeah, I need to have those be the same. This is going to be a temperature increase, and this is going to be a temperature decrease. Right. So I'll come back over here. The mass of the water, C for the water, delta T for the water. Alright, so now we can put in numbers. Alright, 0.385 kilograms and 452 joules per kilogram degrees Celsius. And then we'll have T minus 215 degrees Celsius. And then we'll say equals 1.28 kilograms times 4186 joules per kilogram degrees Celsius, and then we'll have T minus 10 degrees Celsius. All right, that's not too bad. That is one equation, plug and chug. All right, trying to get the whole thing on screen. Our issue is we have to distribute a number between that. So you're going to have some coefficient with T and then some number, and then some coefficient with T and some number. When I did this, all right, I wrote this stuff out. You know, I had a calculator in front of me. That what I saw that I had on the left side, I would have T, and then I would multiply these two things, and I got I forgot the minus sign that should be here. I had 174.02, and it had units, joules per kilogram. Actually, its units were per degree. No, its units were joule per degree Celsius. All right, because it's kilograms canceling. And then I would have minus 37,414 joules. Alright, there the kilograms and the degrees Celsius cancel. And I'll have, on this side, minus, multiply this out, 5,358.08 joules per degree Celsius times T. Alright, it also pays to put parentheses around stuff. This minus and that minus gives us a plus, and 53,580 joules. You can see it can be a little messy, right? You got to multiply this, and then you got to multiply this, this, and this. And you got to multiply this and this, and then this, this, and this. And then the trick here, get the thing with T onto one side, and get the thing that's just the energy, just a number, onto the other side. And when I did this, I got something that looked like that. And then the punchline is that T ended up being 16.5 degrees Celsius. All right, that's the punchline. You do all of this algebra, you get that. It's a number between 215 and 10. And because water is so good at taking the heat out from the steel, it's a number close to 10. Right? But the algebra that you're trying to do, that's the bit where you can make mistakes. And when I'm looking have you done this right? Well, you'll note I drop minus signs. Alright, I'm looking for, is the algebra in order so that you have basically this equation. Right? If you can show you that you can get something that looks like that, then I'm not a judge of algebra skills. I'm a judge of physics. And if you drop this minus sign, right, then you're going to get different coefficients here. You'll get a different temperature. That temperature might make sense. It might not. Right? I haven't run the numbers with that to see will it make sense, but you have to check and be like, well, I got a number like 200 degrees Celsius. That doesn't make sense. I got 400 or minus 400. That doesn't make sense. All right, this number is much more sensible from our experience. You know, we have a cold liquid and we put a hot object in it and it sizzles and boils, you know, like a horseshoe in your homework problem, and it cools it off, which means it's not hot anymore. Right? It's at a lower temperature. So one moment while I switch to a new problem. If you would like to know what's going on with the cats, there's my buddy Spike. He ate some dinner and he's passed out. I'm currently recording this. It's 2:30 in the morning. And I'm going to set up a problem and then we'll come back to that. Alright. So we have another problem. We want to include a phase change in this. And then we'll get to conduction and radiation. Alright. And what we want to look at is we want to melt some ice, or want to melt an object, right? So here we have a bag with some ice, and we have water at the same temperature, and we want to look at those two things, all right? So we want to start with our, we have our container, all right, and it has a mass which is 0.8 kilograms. And it starts out at 0 degrees Celsius. And at the end, we want a container of water at 30 degrees Celsius. Alright. So, if we start out with just water, right? Oops, I just realized you guys couldn't see that, but that's alright. It's just setting up the problem. So, part A for our question is, if we raise the water from 0 to 30, how much heat does it take? Well, that's just the heat is MC delta T. That is all we're doing. We're not melting anything. We want to know how much, once we have cold water, how much to get it warm. And then we know for specific heat, C is 4186 joules per kilogram degrees Celsius. So 0.8 kilograms, 4186 joules per kilogram degrees Celsius. And then our delta T is 30 degrees Celsius because we're going from 0 to 30. And so our heat that we need is almost exactly 100,000 joules. Which I want to say is 100.4 kilojoules. That's a perfectly reasonable way to express that. Right? And because we'll see when we look at the latent heat, when we look at ice melting, some tables use kilojoules as the unit. All right. So for part B, we're melting plus heating. So we start with ice, and then we go to water. So we have to do that in 2 steps. So for the ice, it's going to be the mass times the latent heat of fusion. We have to look that up. Alright, so we go to our lookup table. I'm still on the specific heat. So we go and we find the table for latent heats. Alright, and here we are. There's a bunch of them. What we note for latent heat, that we have 334 kilojoules per kilogram. All right. Hope that came through when I highlighted. It usually shows up. Yeah, okay. So I'm switching back and forth. All right, that's why it looks weird. So remember that our latent heat of fusion is 334 kilojoules per kilogram. And that has some unit conversion here, right? We want to multiply that by 1,000 for joules per kilogram. All right. Or we can leave it in there, but then we have to do some other math. 334, 3 zeros, joules per kilogram. So 3.34 times 10 to the 5 joules per kilogram. This number I have seen in like 8 different ways. It gets confusing sometimes. This is, take that, do the unit conversion, you'll be alright. So, to melt the ice, we're going to have 0.8 kilograms. And then we're going to have times 3.34 times 10 to the 5 joules per kilogram. And we'll calculate that. And I get 267,200 joules per kilogram. Sorry, not per kilogram. Kilograms cancel. And I get joules. So this is for the ice. Right. Now, we're melting plus heating, so the total is the ice melting plus the delta T. Right. Well, we already calculated the delta T. That was this number up here, the 100,464. So we can just add those two numbers. And I'm expressing them in kilojoules so that we get something a little smaller to write. 367.6 kilojoules, or 367,600. There we go. I probably could have rounded a little differently. Yeah, this should probably be a 5, and that should probably now be a 7, but that's fine. Alright, you see how to set the problem up. Alright, so, if there were another phase change, if we had set up and said, oh, well, I want this to become steam at 110 degrees, or if I wanted to heat the ice from lower than 0 up to 0, then I would include other terms in this. But you're just saying, well, what's happening? Well, I'm melting, so I calculate the melting bit. And then I'm heating it up, so I calculate the heating it up bit. And then I add those. I add up all the terms that it is the energy for what's going on. Right? So hopefully that should take care of the problems on specific heat. We're going to want to do heat transport here in a minute. This is a 20-minute video, so we're going to do a third video with conduction and radiation.